Let's look at a problem where we compute the rate of convergence of a function. The function we're going to think about is 1 minus cosine of h over h. And the limit as h goes to 0 of this function is 0. And we want to know how fast does this function approach 0 as h approaches 0. Now, since h is going to 0, we can approximate this function using a Taylor series or a Taylor polynomial about h equals 0. So since h is going to 0, we can approximate cosine of h, really this whole function, but let's just focus on cosine of h for now. We can approximate cosine of h using a Taylor polynomial about h equals 0. So again, h is getting closer to 0, and if we want to think about how this function is behaving as h gets close to 0, we can use a Taylor polynomial about h equals 0. Now this gives us that cosine of h is equal to 1 minus h squared over 2 factorial plus h to the 4th over 4 factorial minus h to the 6th over 6 factorial plus etc. We continue in that pattern. Now, because cosine has this pattern of even powers of h, you can think of this as like h to the 0. Really, instead of this first term being the 0th Taylor polynomial or the constant polynomial, because the error term that shows up next is the square, this is actually, we can think of this first term as P1, it's the first Taylor polynomial, because there is no factor of just h by itself that would have shown up. The next terms give the remainder. If I were to write out the remainder term for P1, it would encapsulate all of the rest of these, infinitely many terms. So this is really sort of capturing R1. Similarly, if we had just looked at these first two terms, because the next term is h to the 4th power, that tells us that this is actually P3, and the remaining, infinitely many terms would be encapsulated in R3. Okay. So let's look back at our original problem here. The numerator of our function, 1 minus cosine of h, so I'll say then the numerator would become, and when I say numerator, I mean the numerator of this function here, 1 minus cosine of h, but I'm going to replace cosine with this whole expansion. So 1 minus h squared over 2 factorial plus h to the 4th over 4 factorial minus, etc. And so I end up with these two 1's adding up to 0, 1 minus 1, and then I have the rest of this expression. So I'll end up with h squared over 2 factorial minus h to the 4th over 4 factorial plus h to the 6th over 6 factorial, etc. Now, this is why I sort of made this point here. The remainder, of all these terms that are left over are encapsulated in R1. So that gives us the hint that we should be thinking about computing R1. So the remaining terms can be captured by R1 of x, that remainder term. So let's go ahead and compute the remainder for this polynomial. Let me go and get a new slide here. All right. So we want to consider really, instead of expanding cosine of h with all of those terms, we just want to think about P1 of h here instead of x plus R1 of h. And I think back here I might have put x instead of h, so let me go ahead and clear that up. This should really be h. Sorry about that. Okay, let's go back to this slide. All right, well, P1 we just saw is 1, it's that first term, and the remainder will be the second derivative. Here I'm calling cosine f of h here. I know that's not the full function that we're considering in that limit, but let's just call this f for now. So this is f of c of h over 2 factorial times h squared, where c of h is some value between where we're expanding about, so between h equals 0, and then where we end up evaluating this function. Okay, so we don't know this c term, and that's sort of what allows us to combine all of those infinitely many terms that we would have had if we had expanded this, to however many terms we wanted to. So really, this encapsulates all of that. The second derivative of cosine, so let's see if I have f of h is cosine of h. The first derivative is negative sine of h. And the second derivative is negative cosine of h. So let's go ahead and substitute negative cosine of h here. I'm going to write c though, because I am evaluating at c of h. So I have 1 plus negative cosine of c of h over 2 factorial h squared. And instead of writing plus and negative, I suppose I can just write 1 minus. Okay. All right. Now let's go back to that original problem we were trying to solve. We can say that the rate of convergence, is then computed as, and you'll remember in the definition that we saw in lecture, this was that capital F of h minus L. In our case, capital F of h is 1 minus cosine of h over h. And L is 0 in this case. So when we compute this, I'm going to replace f of h with 1 minus cosine of h over h minus 0. That's our limit. And I'm just going to substitute in, for cosine of h, I'm going to substitute this expression. So I have 1 minus, and then in this expression I have 1 minus cosine of c of h over 2 times h squared. All of that is still over h, and I'm just going to leave out the minus 0 because I don't need to write it anymore. Well, let's expand this out a little bit. I'm going to end up with 1 minus 1 plus h squared over 2 cosine of c of h all over h. Oops. And again, these ones, 1 minus 1 is 0, so I'm left with this expression, and one of these factors of h can be canceled with the denominator. So here I'll have absolute value of h over 2 cosine of c of h. All right, now cosine, and sine for that matter, if this had been a sine term, we could do the same thing. Cosine can be bounded by 1 in absolute value. So the highest it can get is 1, the lowest is negative 1. And because we don't know much about c, that's sort of the best we can do at this point. So I'm going to say this is less than or equal to h over 2, really times 1 for that cosine term, but I don't really need to write that 1 down. You can if you want. So I'm bounding cosine by 1 there. Now I have my expression. I have, some power of h times some constant. So then 1 minus cosine of h over h is equal to the limit, in this case 0, plus big O of h, so that power of h I have here is just h to the first power, for sufficiently small h. Or if you like, you can just say that the rate of convergence is big O of h. All right, I hope you found this video helpful. Let me know if you have any questions.